Okay, so last time we spoke about average rate of change. We pretty much finished that section. There was nothing really else we wanted to talk about. We just needed that one formula, which is pretty much the difference quotient. Exactly like the difference. And we're going to use that again later as well. So last time we officially started calculus, we're in chapter 2. So we started talking about rates of change. We're going to actually make that more precise later on by the time we get to section 2.3. And for now, we're going to go to 2.2, which is the study of limits. So we're going to find our limits today. Super important. So, lecture 2 we spoke about what calculus was about, attacking two main problems, the rate problem, how fast something is moving, and the area problem, how much space something takes up. Told you that the derivative is what deals with the first problem, and the integral is what deals with the second problem. It turns out that both of these tools are actually limits. So, if I had to sum up calculus in one word, it would be limits. What is calculus about? Limits, that's what it's about. Right? Because the two main tools that we use, they're actually limits. They're formulas using limits. And so now we're going to talk about what limits are. How you want to think about limits, it's about getting close. Getting quite intimate. Right? So that's what limits are about. So let me explain the idea that we want here. Definition, the 205 definition. The actual definition is a lot more complicated, which we don't need to get into. But we're just going to use a workable definition for our purposes. We say, let me explain the phrase while we say the limit of a function f of x is L as x approaches a. And you write this symbol, Lim, x approaches a, x equals L. If, as x gets close to a, f of x will get close to L. And that's good enough for us at this point. But a mathematician would hate a definition like that because it's not very precise at all. What is being close? You know, within 1 unit, within a half unit, within a quarter unit. So the full definition actually tells you exactly, precisely in mathematical terms what it means to get close to something, but we don't actually care. Right now, the intuitive idea is enough for us. We're not going to be proving anything. We're going to be just computing stuff. And so basically, this is what we want to know. So yeah, the limit. So that's the definition. You want to remember what this means. You look at some bullet points. So one thing you want to notice is that limits track y-values. Right? The limit is a y-value. That's how you're going to want to think of it. You're looking at the outputs. Limits tell you what the y-value gets close to as x gets close to some number. Another important bullet point. is that we do not require that y equals f of x is defined at x equals a, right? Because limits are about getting close to something. We don't actually have to get there, right? That's the idea that we want to emphasize. We're talking about getting close to some point, not actually even getting there. If we get there, that's great, but we do not have to. But the thing is, while our xy is approaching some number, we want to look at what the y value is doing. And later on, we're going to see why that's important for us to know. But that's basically what a limit is. Getting close to something, you want to see, as you move the x value, what the y value is doing and if it's approaching something. So let's look at some of those statements. So, what if I ask what is the limit as x approaches 1 of the function f of x? Right, so let's look at our picture first. So then this is my function. And curve. And I know at 1 it goes to 3, let's say at 2, it goes to 5. Goes on further that way, so this way. And so I ask you this question: what is the limit? So you'd actually read that. Let me emphasize how this is done. The limit as x approaches a of f of x. That's how we read it. Right? So here's a picture. It's just a graph. You don't have to know the formula right now. We're just looking at the idea. Right? So I could ask you, for example, what is the limit as x approaches 1 of the function f of x, where this is your function y equals f of x. In other words, I'm asking you, what is the y value that this function gets close to when your x value gets close to 1? Right? It's exactly the same thing that I'm asking. So what would your answer be? 3. So now you look at this and you're like, okay, so my x is getting close to 1. Notice that when I approach, my x value approaches this number, my y value will approach that number. Right? My y value will approach 3 when my x gets close to 1. Right? Now in this case, I could actually be there. I could actually be at x equals 1 because the function is defined there. And I can just realize that f of 1 is 3, and I can say that's the answer. I would get exactly the same answer though if my function was actually not defined there. So if that was a 3, that was a 1, and I ask you, what is the limit as x approaches 1 of f of x? The answer would still be 3, right? I do not care that I can't actually be at 1. I just care, as I'm getting super, super close to 1, what is the y value getting close to? Right? That's the idea. It's about closeness, right? As my x value is approaching something, what is my y value approaching? Let's do another illustration. So now I ask you, what is the limit as x approaches 1 of x? 2. What's the answer? 2.
3. 3.
3.
Would be 3.
Is it 2 or is it 3? 2. 2.
It
Who thinks
doesn't
it's 2?
matter.
Who says 2?
It doesn't matter.
Who says 3?
It doesn't matter.
Did you guys put up your hands last night? Okay, who says 2? Come on, quick. Stand up and be counted. Okay, who says 3?
Is that an option?
Okay, who says it's another option?
Yeah.
What would the other option be? Huh?
2 or 3.
Both?
No, 2 or
Because
3.
one is going in the like the opposite. They're like going in the opposite direction.
From left to right.
Or does it matter?
It goes to another.
Do it either be 3 or just not exist? I'm not sure.
It could be 2
1, 2, and 1, 3. Yeah. Is it 1, 2, or 1, 3?
Just give us the answer.
Okay, so what is the definition of the limit? What did we say it was?
When you get closer to the limit. So as x gets closer to 1, y gets closer. Right, there's a 2 and there's a 3. But look,
Right,
the
well,
3.
so here's the thing. The answer has to be definite in some sense,
Okay, so 3.
right? So if you look at this and you're like, okay, what if I'm getting close to 1? What is the y value? Well, you're like, well, if I'm approaching 1 from here, the answer is 2. And then, but if I'm over here and approaching 1, the answer is 3. So now the idea is, well, is the answer 2 or 3?
So it's 3.
Is it both?
It's neither. Right? So remember what we're asking. What we're asking when I ask you this is, what is the y value?
You don't know.
Right? There is no the y value. Well, sometimes it's this, sometimes it's that. Right? That idea is actually not good enough for us. We actually need a definite answer. Right?
So the limit doesn't
So
exist then?
what we would say here,
Undefined.
in this case, we would say the limit as x approaches 1 of f of x does not exist. You could say undefined, but it's kind of weird to use that phrasing. Most people just say it does not exist, or you can write DNA as an abbreviation for does not exist. Right? Because there is no the y value. When you're asking for a limit, you're asking for some definite answer. Okay, what is the y value approaching? You need an answer. What?
Did you change the circles for a reason?
Oh no, that doesn't even matter.
Wait, but I have a question.
Like I told you, we don't care about being at the point. I don't care that this is shaded or not shaded. It's irrelevant to me. I don't, because I never actually care about actually being at 1. I care about getting close to 1. Now the idea is here, it seems that it depends on the direction, right? And somehow that answer 2 or 3 is not satisfying folks, right? So for example, imagine if we had a situation like this, where this is 1, and over here, this gives you 100, and over here, this gives you minus 300. And for example, let's say y is in units of millions of dollars. And I say to you, okay, I'm going to do this business venture, do your analysis, tell me how much money I'm going to make. Well, you could make 100 million or lose 300 million. You see, that's not going to be satisfying to me. Right? I'm going to need to know an answer. What do you mean? What does that mean? Right? Well, in that case, you'd have to go further and you say, well, if you try this strategy and this happens, you could lose up to $3 million. But if you try this strategy and this happens, you could make 100 million. Right? So I can't get my definite answer, but there is some sort of answer that depends on the direction you're going. So that is the idea of a one-sided limit. So there's a limit, that's an overall limit where, this is it, this is where the y value is going, we know the answer. But there's sometimes when the answer kind of depends on the direction, and you call those one-sided limits.
Jhevon,
Yes?
how would you know in what direction it's talking about then?
Oh, that's what I'm going to tell you. I'm going to tell you about that. last example brings up the notion of one-sided limits. Right? These are where the answer depends on what side you're coming from. Right? So here's the notation for one-sided limits. So it looks very similar to the original notation, but we put actually signs in the powers. That's the notation. So if I put a plus sign here, a to the plus positive power, right? That actually means the limit as x gets close to a from the right side, right? So a plus means you're a little bit bigger than a. You're a plus a little bit, right? So it means you're on this side of a. So that says you're approaching x from the right side. There's a similar notation, a with a negative sign in power, f of x, is limit as x gets close to a from the left side. Right? So these are called the one-sided limits. So there's a difference between an overall limit, where I have a unique answer, and there's a difference between a one-sided limit, where the answer can actually change based on which side I'm approaching from. So, in that case, redraw this diagram in your book right now. Because I'm not going to redraw it, I'm going to start talking about it. So redraw that diagram, the same diagram you had before. So now, I can ask you the following question. What is the limit as x approaches 1 from the right side? And I could also ask you what is the limit as x approaches 1 from the left side? Now, according to this picture, now you can sort of look at it in a different light, right? There's no one y value that you're approaching, so you can't say the limit is this y value, right? However, if I look at 1 and I think I'm approaching 1 from the right side, so my x values are getting close to this. So once I'm on the right side, I go on the curve, right? So I'm on this curve, walking to 1, right? So if I'm on this graph and I'm approaching 1 from the right side, notice that the y value is getting close to 3. The closer I get to 1 from this side, the closer the y value gets to 3. Right? So as I approach 1 from the right, the answer is 3. Similarly, if I'm on the graph over here walking towards 1, my x value is getting towards 1. As I get close to 1, my y value on this side is getting close to 2. So I can say the limit as x approaches 1 from the left side of f of x is 2. Now, we can define, which would be equivalent to the previous definition, limit of limits in the following way. Do I want to call it a definition? Let's say we can look at it. Limit as x approaches a of f of x exists if both the limit as x approaches a from the right of f of x exists, both the limit as x same value. So the idea is the only way to have a unique y value that your x approaches is if these two sides actually connect, right? Not literally connect, they could be a hole at that point. But they have to sort of approach the same y value at the same time so that whether you're coming from this direction or that direction, you're getting the same answer. That's where the overall limit, it makes sense to say, oh, this is the y value, here's your answer. And there are other cases where, well, it depends on what side you're approaching from. And you are going to want to distinguish between these two. Right? This idea of connecting things is going to be important to us, so that's why we want to have a mathematical way to say two sides of a function connects or it doesn't connect. That's kind of what we want to get at. Any questions on that idea? Right, so a limit is like the y value you're approaching when your x value gets approached to something. One-sided limits only cares about one side at a time. So the positive notation says you're approaching from the right side. The negative notation says you're approaching from the left side. And these could, in theory, give you two different y values. And in the case that they do, the overall limit does not exist. In order for the overall limit to exist, both sides have to agree on the y values. So,
Are we going to see a case when both we have an overall limit for a graph?
oh yeah, we're going to make things a lot more nice. So let's look at this function. So here I was just showing you from pictures. Let's actually look at some concrete examples and let's make it actually nicer. So consider this function. What is a limit as x approaches 1 of f(x), limit as x approaches 0 of f(x). Let's do 0 from the left. Limit as x approaches 2 from the right. Here I gave you a function, 1 over x is the function that we're looking at, and I want you to find all these limits. So here, x approaches 1 of x. What do you think that's going to be? It's going to look like 1. You can see clearly from, you can kind of like even plug into the formula. As x gets close to 1, this 1 over x would get close to 1 as well. One way you can look at that is, again, from the picture. We can see if we're just plotting the points on this function, 1 would correspond to the y value 1. So whether I'm approaching from the left or the right, my function, the y value, is getting close to 1. Whether approaching the left or the right. Right, that's my picture. And it seems here that, hey, I could have just plugged that in, right, which we're going to talk about later. So that's actually 1. What about B? So here's our function. What is the limit as x approaches 0 from the left side? What do you mean? What's happening to 0? What is that happening at 0? Okay, but do I care about actually being at 0?
No.
I care about being close to 0. So if I get close to 0, what's actually happening to my y values? Remember, you want to think of your limits as tracking the y values. What is the y value doing? Decreasing. How far? To what? Right, it's going to keep decreasing forever, right? It's never going to actually hit 0 or any negative number. It'll keep getting lower and lower, right? So in this case, if our function decreases without bound, we'd say it's limit is negative infinity, right? Now this answer will be meaningful to us to some extent. We don't want to say like there's no answer when there really is some sort of behavior that we might want to point to, like no, things are going downhill, right? So in this case, we could say negative infinity. It's possible to have infinity as an answer to a limit. Right? Okay, let's look at C. Limit as x approaches 2 from the right side. Here's my function. So now I'm approaching 2. Now when 2 with a little plus means 2 from the right side, so I'm only considering here, right? Meaning I can literally ignore the left side of the graph. I can ignore all of this. I only care about getting to 2 from the right side. Now what's going to happen to the y value? Right, so I know 2 corresponds to what y value in this function, 1 over x. 1/2, right? 1 over x is 1 over 2. And so whether or not I'm at that point doesn't matter. If I'm approaching here, the x value is approaching 2, the y value is approaching 1/2. And again, it seems to me that I could have just plugged in 2.
I don't understand. How does it approach to 1 and 1/2 there to the half?
Oh, because that's the function. Right? If I were plotting points, then if I plug in x equals 2, the y value would give me 1/2.
Okay.
So you plug 2 from
Oh.
So technically you do plug in for x. So then the 0 is 1 over 0.
When do you plug in?
They're telling you from the left side.
That would be 0.
It's a minus 0.
Yeah, so we're going to get to that. You guys are always going to.
So C is 1 passive.
Yeah, so obviously you couldn't have plugged in 0, which is why the answer to this one is kind of crazy when you think about it. Like infinity is the answer. It's not even a number. But let's actually look at that. So I'm going to talk about cases on how to evaluate limits as well. But I just want you to get used to the idea of watching what the y value does when your x value is doing something else. There is a part D though. So let's actually look at that one.
Does not exist.
Limit as x approaches 0 of 1 over x.
Does not exist.
What do you mean it does not exist? Can it be like infinity?
But it's approaching negative and positive infinity.
Coming from the left.
So the limit coming from the left was what?
With negative.
Okay, principle.
That was negative infinity. Okay, so why?
So then the other one will be positive. Well, infinity.
Oh, well, if I'm on the graph approaching 0 from the right, yeah, you are right. That's infinity.
Yeah, but
So
you're
that
the
x
direction.
approaching 0 from the right side would actually give us plus infinity.
So then it
In
doesn't
this
exist.
case, you don't know. It's neither. Do not.
So what's the y?
Yes,
What's the y?
it doesn't
Am I making an infinite amount of money or losing an infinite amount? Those two are great. They do not. That means they don't agree. The limit as x approaches 0 of 1 over x does not exist. Let me ask you another question. Limit as x approaches 0 of 1 over x squared. What is that?
Same thing.
Okay, so 1 over 0 squared, what is it? It's like the
You
same.
can't plug in 0.
You said you don't plug in. Did you not just say
No, you can't plug in 0. Plugging in 0 doesn't make any sense.
But x is, so then it does not exist.
It'll be positive.
Who says it doesn't exist?
Wait, I need to grab it.
I'm saying I'm giving you direction, doesn't it? No, so it doesn't. It's not either positive or negative.
Positive.
Let's look at the picture. What does 1 over x look like?
Like this. It'll be positive.
What the?
That's 1 over x.
I mean, oh, like you guys didn't know what that looks like. You guys should know what it looks like. So as I'm approaching 0 from the left side, what's happening to my y value? Increasing without bound, I'm going to positive infinity. So as I approach 0 from the left, I get plus infinity. What if I approach 0 from the right?
It's also
it again approaches positive infinity. They agree, I define the limit to be that answer. As I get close to 0, no matter what side I'm coming from, the graph is blowing up. So that's tracking the y value. What's happening to the y value when I get close to 0? It's going to infinity. I go from the right, it goes to infinity, go from the left, it goes to infinity. The y value overall is going to infinity.
So what if we just say with like, if it was x squared, like it would still be.
If x squared?
If it said if it instead of 1 over x squared, if it was x squared, it would be the same answer.
Not 1 over x squared, just x squared? Like the limit as x approaches 0 of x squared? What would that be? That's actually 0. Because I can literally plug in 0. There's
Oh, but
one-
now you can plug it in.
The other way to look at it.
Wait, now you can plug in 0?
So when can you not plug
Oh, yeah, well, yeah.
Well, remember last time you never divide by 0, so you never even think of plugging 0. But here, look, when I come from the right side, the y value is approaching 0. If I come from the left side, the y value is approaching 0, the limit is 0.
Professor?
Yes.
For E is, there's no,
Does not exist.
yeah, does not exist because they're both going in opposite directions.
It's because the left and the right do not give the same answer.
So when they're never the same, so it's just Z and
Right. In order for the overall limit to exist, both the left and right side must have an answer, and they must be the same answer.
Oh, okay, okay.
By the way, it's possible for one side to not even exist at all. That's actually possible. So, I could give you an example where it's not even possible for one side to exist. I did tell you guys what the graph of the logarithm looks like. It's common teaching two of the same class. Sometimes you don't remember which class you told what. Gonna go to my other class. Didn't I tell you guys what a logarithm looks like? No, because you didn't. Oh, okay. Right, so look at the graph of logarithm. It's funny. Sometimes you ever had those situations where, in hindsight you wish you said something else? So it's not all good. It's not all good for you guys. There's sometimes I'm like, I probably should have told them. And I go to my second class and tell them. Like, this is my chance to go. Okay. Luckily for you guys, I repeat myself so often, it doesn't matter if I forget to tell you now. I'm going to tell you down the road. Okay, so here's the graph of logarithm, a random log. Let's say ln, the natural one, because we like that. I could ask you, what is the limit as x approaches -1 from the left of ln of x? And that answer would be, does not exist. Right? So even a one-side limit doesn't have to exist, because if I'm over here at -1, the graph isn't even there. Like, what am I walking on, right? I can't, there are no y values, right? What are you talking about, track the y values? There are no y values there, right? So I could say it does not exist. So it's possible to have infinity as an answer for either side or the general limit. And it's possible for either side to not exist. And of course, if one side does not exist, the overall limit, of course, would not exist either. So now by just looking at the pictures and seeing what's happening to the y value, we did get to some sort of notion of how to compute limits. There seems to be sometimes you can just plug in the x value. Just plug in the x value. Oh, wait, before I talk about how to compute one in general, let's look at another. That would be nice, a very interesting one. Let's look at this guy. What's the answer? Is Is there an answer?
I have 8.
There's a hole in the graph.
So x plus 2, it's like having x plus 2.
It's like having x plus 2.
Yeah, so the limit of x
If you do
equals
minus 2,
2,
that's
x
0.
plus 2.
Yeah, it's
So
zero.
that is how you cross that out.
No, there's
So you're saying we should do something like this.
X plus 2. That's it.
Yeah. Cross that out.
And I can,
yeah.
yeah.
But that means that there'd be a hole on 2.
And so you would think that the answer is 4.
No. Who's square that?
Does that actually make sense?
I think it doesn't.
Well, how would you kind of convince yourself? Like,
Go back to the original graph.
Because
could you try to graph it? Sure. Just actually try to graph it, see if the picture would agree with our answer, that it gets close to 4. So, how do you graph that?
It's a linear.
You gotta get the
It's a
interval.
linear.
Oh, it's
It's a linear function.
if it's exponential. Okay.
You could divide it.
I think that it's a no.
You think it's a no? Like, there's no answer?
No, it's 4.
So, here's how we can think of this guy. Now, if I'm looking at the graph y equals x squared minus 4 over x minus 2, I know that if x actually equals to undefined, right? Doesn't have an answer. So at 2, I can't actually plug in 2. There's literally no answer, right? However, what if x is not 2, right? Then I could just do this. Then it's a regular fraction. The denominator is not 0. All my rules for fractions work. I can just factor things and cancel things. Arithmetic will still work here because I'm never divided by 0 at any point. It's just a regular fraction at each x value. And so I can literally simplify this to x plus 2. Now what does the graph of x plus 2 look like?
It's a line.
Okay, how does it look?
Like diagonal line.
By 2. By 2.
Two is the line.
Right, so the y-intercept is 2.
Then
Goes through that point. Okay, but if my x is 2, what's happening? It's undefined, right? So at 2, what's going to happen is this gives us a hole. It actually can't exist at that point because division by 0 is never going to work. So it looks like x plus 2, except it has a point missing, the point when your x value is 2. So now you can ask the question, well, what if I get close to 2 from the left side of this function? Well, it's getting close to 4. And what if I approach from the right side of the function? It's getting close to 4. So this answer actually makes sense. The limit of this guy as x approaches 2 is actually 4. Now, never mind that I can't be at 2. Remember, limits only care about getting close to something. You don't have to actually be there. I cannot actually plug in x equals 2 because that's divided by 0. It doesn't make any sense. But I can get as close to 2 as I want. I can be 1.99999 or 2.01, right? I can get super close to 2 without actually getting there. And at all these numbers, the y value will get close to 4. So this answer actually does make sense based on our definition of a limit. Remember, we don't actually have to be there. We just need to get close there, super close.
Then you want to simplify. Thank you.
Yeah.
Right?
What?
Or then aren't you allowed to simplify a function then? If, let's say if it's
Yeah, so now I'm going to tell you the general approach that you want to take with limits. So I give you a problem, say, hey, find this limit. Right? The first thing you're going to try to do, you're going to try to plug in computing limits to compute limit as x approaches a of f of x Step 1, if f of x is defined at a, right? Meaning I can literally plug in that number, I can find f of a and it's an actual value. Then the limit as x approaches a of f of x is just going to be f of a. In other words, I can just find the limit by plugging in the number, right? The caveat is it has to be defined there. So it can't be something where I plug in and it divides by 0 or it gets an asymptote or something crazy happens, right? So as long as your function is defined at the point, then if you want to get close to the value, the best thing is to actually be the value. How much closer can you get, right? And that will actually give you the corresponding y value for that function. So in the cases where you can plug in an x value, plug in the x value. That's all there is to it, right? And that's what happened with y equals the limit as I approach x squared. X squared is a polynomial, so we know the domain is everywhere, so I can literally plug in any number I feel like. And now you ask me the limit as I approach 0, it's just going to be 0 because I can just plug it in. That falls under category 1. This is called evaluating limits by continuity. Which I'm going to tell you guys about continuity. So we will come back to that very briefly. It's an important concept, but I don't think I'm going to test it on, but I'll just mention it. All right, so there is one case where I'm talking about approaching some value. If your function is actually defined there, just plug in the number, and that's going to be it. And then, so even that guy that seems to have a problem, like if I actually what's the limit, x squared minus 4 over x minus 2, and I'm approaching 1, hey, it's defined at 1. I can really just plug in 1. And that would actually be the limit, so that's minus 3 over minus 1. The answer would actually be 3. Because there is no problem at 1. The only thing I cannot plug into this function is the number 2. So if I'm approaching any other value, literally just plug it in, and that would be my answer. I don't need to figure out what the graph looks like or anything. If I'm given a formula, and the formula works at some number, just plug in that number. That's the y value you're going to get close to. Now I deal with the second case. If f of x is not defined that way, meaning it doesn't make sense to plug in a into that function, then there are two cases. So this is 2a. One, f of x can be simplified. Here's where you're going to do your algebra. So that it is possible to plug in x equals a. In this case, do so. So that's what happened with the example. X approaches 2 of x squared minus 4 over x minus 2. Right? So technically my function is not defined at 2, but I could actually simplify it so that it is defined at 2. And so at that point, I really just plug in x equals 2. Right? The idea is, this simplification really just creates a hole in the graph, but the truth is, I don't care about actually being at that location, so having a hole is actually fine. So there are cases where it's not defined, and basically all it means is there's a hole at that point. And in that case, whenever a situation like this happens, what that means is you'll be able to simplify algebraically and cancel the part that's giving you the problem. So 2a covers this situation that I just erased. So there are times when your function works at the point, just plug in the point, no problem. There are times when your function doesn't work at the point, however, algebraically you can simplify to get it to work. And in that case, it's valid to do so, because all it means is there's a gap at that point, and I don't care about being at the point, so a gap doesn't bother. A hole doesn't bother. And there's 2b. In the case f of x cannot be simplified, in this case, three things will happen. One, you will have the limit is going to give you an infinite answer. Two, the limit can give you a negative infinite answer. Or three, the limit just plain old does not exist. So in these two cases, in case 1 and case 2, part A, the limit actually exists, I can get an answer. In this case, it can go either way. The limit can exist, but it will be infinite in some direction, or it just won't exist at all. And how you figure that out is, if the graph is known, watch the graph. The y-values, right? That was the case with y equals 1 over x and y equals 1 over x squared. So technically I couldn't So there was a problem with plugging in the answer, but at the same time, I can't actually simplify it. I can't cancel the x, right? There's nothing I can do. There's no algebra I can use to get rid of that x in the denominator, which is a problem. So what do? I look at the graph, and I can see as I'm approaching 0 what's happening. This side is giving me a different answer from that side. Or in this picture, I can see that this side is giving me the same answer as that side. They're both infinity. So in this case, it does not exist because I can see the y values are doing something different. In this case, it does exist because I can see the y values doing something, the same thing. Right? So I can actually look at the graph and just track the y values, and that will determine if it exists or not and what it would exist at. If given the formula, but you're not sure what the graph looks like, plug in values close to A. On both sides of A and track y values that way. Which is almost never going to be the case. In this class, I'm basically going to cover everything up to this situation, but you should know that this situation actually exists. If you, frequently exam and forget how to graph 1 over x squared, you can do this method, and I'll forgive you the first time. So then just make sure you never forget what graph looks like next time. So what do I mean? I literally just do a table of values. So I can see, for example, if I look at the x value and I look at y equals 1 over x, and I want to get close to 0, I'm just going to plug in numbers that are super close to 0 from either side, right? So I can plug in minus 0.001, minus 0.0001, minus 0.00001, and from the other side I can plug in 0.001, 0.0001, 0.00001, and so on and so forth. Now if I'm over here, you'll notice I'll start to get answers like minus 100, minus 1,000, minus 10,000, right? And then over here, you'll notice that these guys are just approaching negative infinity. They keep getting bigger and bigger and bigger. They have no sign of slowing down. Whereas from this side, I will get 100, 1,000, 10,000. Right? You'll see from this side, the numbers just keep getting bigger and bigger and bigger in the positive direction. These guys aren't matching up, so I can look from the tail and realize, oh, the limit's not going to exist. As I'm getting close to that 0, which I actually can't plug in, but as I plug in numbers consistently getting close to it, I can see that there is no pattern that the numbers are following. So you'll figure out from this that limit as x approaches 0 of 1 over x does not exist. As opposed to if I had 1 over x squared, and I'm plugging in minus 0.01, minus 0.001, minus 0.0001, and here 0.01, 0.001, 0.0001. Then as I'm coming from here, I'm going to have and these are actually going to give me exactly the same numbers. Because I'm squaring, I'm getting rid of the signs. I realize that here, the numbers just keep getting bigger and bigger. They're going to infinity. When I'm approaching here, the numbers keep getting bigger and bigger. They're both going to infinity, right? So at this point, I can just say, hey, the numbers just keep getting bigger and bigger when I get close to 0. They show no signs of slowing down, so from this I can conclude that as x approaches 0, 1 over x squared is infinite. And you could do that similarly to with this guy, y equals x squared minus 4 over x plus 2, x minus 2. And you want to approach the value 2, so you can plug in like 1.9, 1.99, 1.999, or you can plug in 2.01, 2.001, 2.0001. The idea is you want to get super close to 2, and you realize that both are converging to the number 4. If you start plugging those in and actually working them out, writing these as fractions, you'll see that you're getting close to 4. This will give you like 4.01, 4.001, 4.0. This one will give you 3.9, 3.999, 3.99999, 3.999. You see that they're both actually getting close to that number 4. Right? And so you can actually, I'm not going to write down the values because I don't feel like computing, but you can see from the values that, hey, the y values seem to track towards this number. Right? So if you don't know what the graph looks like, you can actually start plugging in values and seeing what the y value is getting close to. However, in most cases, what I'm going to give you for limits, at some point you'll either be able to simplify it, directly plug in the number, or you'll be able to draw the picture and just watch what the y values are doing from the picture. So that covers how we're computing limits. So here, let me just summarize. So I told you the cases, so let me just give you the strategy. Given a random unit problem, first thing you're going to try to do, try to plug in the next value. If that doesn't work, try to simplify. Meaning algebra. Try to factor things, cancel things, rewrite things, move things around in a mathematically coherent way. Try to simplify it so that you can plug in the next value. If that doesn't work, track the y values from the graph or by plugging in numbers closer and closer to A. So that's your limit strategy. Limits I'm definitely going to ask you about. It's coming in tests and it will be on the final. So there are going to be problems where I just ask you, compute this limit. I'm going to ask you, limit as x approaches whatever of some function, and you're going to want to figure out what the answer is, and this is going to be your approach. The first thing you're going to do is you're going to try to plug in the value. But that might not work. Maybe when you plug in that value, you divide by 0, something crazy happens, or there's a negative under a radical, or something crazy will happen. Right? So for this, you're going to need to know about domains, right? Where the function is going to work. Right? So if your function, if that x value is in your domain, just plug it in, and that's your answer. If that doesn't work, try to simplify, right? It's a fraction, you can factor and cancel stuff, and hopefully that works out. But what if it doesn't simplify, like 1 over x? 1 over x, you can't simplify that. Then you start to look at the y values, look at the graph, look at what the y values are doing on the graph. If you don't know what the graph looks like, start plugging in numbers and realize that the closer I get to this number, this is what's happening. Right, so that's the strategy.
Wait, did you say this is going to be on the test?
Yes.
The one on Thursday?
No, we're in chapter 2. The one on Thursday is only chapter 1. We're beyond that test. Okay, great. So, the definition tells us this, function number 5. So now, let's talk about. Okay, let's talk about some properties. Computing limits for more and more complicated things, because we always want to build on our understanding. So here are some properties of limits. It turns out that assume C is a constant and limit as x approaches a of x and the limit as x approaches a of g of x exists. And we need two functions for these. Then the following hold. a constant times a function is just going to be equal to a constant times the limit of the function. So, just a silly example. Let's say I ask the limit as x approaches 1 of 2x squared. Well, that's just the same as 2 times the limit as x approaches 1 of x squared, which is just 2 times 1, which is 2. Or you can literally just think of it as plugging in 1. Right? But you should know that constants, factors, we don't care. You can factor them out or just plug them in. It won't matter. 2. The limit as x approaches a of the sum of functions. That's f of x plus or minus g of x. Then I can just take the limits separately. I can take, this is just going to be the limit of f of x plus or minus the limit of g of x. Another, limits distribute, right? Not everything distributes, so I have to tell you things that do distribute. Remember, logs do not distribute. But limits do. So if you have the limit of a sum, it's just the sum of the limits. Limit as x approaches 1 of the function x squared plus 1 of x. Right? Which might give you a headache to graph that you don't really want to. But what can happen is you can just think of it as the limit of x squared plus the limit of 1 of x, which is going to be 1 plus 1, which is 2. Or again, using number 1 from here, I could just plug in the number 1, and I get the answer 2 as well. But you can know that to find the limit of a sum, you can just look at each individual component, plug in the numbers, find the limits, or do something. The limit as x approaches a of a division of functions is actually equal to the limit of the top divided by the limit of the bottom. If the limit of g happens to not be 0, because you can never divide by 0. So I can say, for example, here, limit as x approaches 4 of radical x over x plus 1. Well, I can think of that as the limit as x approaches 4 radical x over the limit of x plus 1. So that's going to be 2 over 5 will be the answer. Right. So again, as long as I can plug in a number, just plug in the number, so you can look at the top separately from the bottom and evaluate it at that point. So limits have very nice properties. They distribute across sums, they distribute across divisions, you can factor out constants, and they distribute across products as well. So if I have the multiplication of functions, that will also work. Limit as x approaches a of f of x times g of x is just going to be the limit of the f times the limit of g. So, for example, here, what is the limit as x approaches 3 of x times the radical of x plus 1? So here I can think of this as two functions multiplying each other, the function x and the function radical x plus 1. So that's just equal to the limit of x times the limit of the radical x plus 1. So that's going to be the 3 times 2. So it will be 6. Questions so far? So these properties are really nice with limits. They kind of work as you would expect numbers to work. You can factor things out, you can distribute across sums, distribute with all rules. distributes across divisions, distributes across products. Of course, the caveat for division is always you can never divide by 0. So if you're plugging in something and your denominator is 0, you're in the case where you have to try to simplify and cancel and try something else. There's a fifth property, it's going to be nice for us, is exponentiation. Limits actually distribute across exponentiation. So that the limit as x approaches a of f of x is raised to the power. That's just the limit of the inside raised to that power. Example, the limit as x approaches 2 of x squared plus 1 cubed. Well, that's just the limit as x approaches 2 of x squared plus 1, and then I cube that answer. So that's going to be 5 cubed, which is 9. Which again coincides with law 1, the strategy number 1, where I can really just plug in, this is a function that's defined at 2, I can just plug in 2 and get the answer. But these properties are important in the proofs of things. What else do I want to read about? Not continuity, maybe some other. Yeah, so those are the properties that work. What are we talking about? Maybe another technique. But this kind of falls under the simplifying to cancel something bad technique. So you can use things like rationalizing. So I can use something like the limit. X approaches 0. So here you can't plug in 0, and at first glance it might look impossible to simplify that, but it turns out that we can simplify that by rationalizing. So we're going to use kind of the same trick that when I asked you to find the difference quotient of the square root of x. So what can we do here? Multiply by the conjugate of the numerator to see if something like that will work. Minus 2 plus. So I multiply and divide by the conjugate, and let's see what happens. Okay, so what happens to the numerator? I get 4 plus x minus 4. Right? So notice that the top just looks like the difference of two squares formula, a minus b times a plus b. So the answer is a squared minus b squared. So I just square that and square that, and I get that. All over x times 4 plus x. So what happens is 4 minus 4, the 4's kill each other, now I have an x in the top and an x in the bottom, those will cancel. So I would then get the limit as x approaches 0 of 1 over 4 plus x plus 2. And now notice there is no problem with plugging in x equals 0. So I can just plug in 0 here, radical of 4 is 2, plus 2. So the answer is 4. So pretty much any simplification idea of all your algebra you have to remember here. Because you might have to rationalize, you might have to factor, you might have to do any algebraic operation you should be able to do it at this point. So let's talk about infinite limits.
I have a question.
Yes?
You know how you cancel the 4 and the x?
Mhm.
Is that?
No, I canceled the 4 minus 4, so the 4 went away.
But isn't the 4 with the x? Because it's addition.
Well, distributive law, right? So I can expand the brackets. Right, the top is just 4 plus x minus 4. I can add it in here. So I expand these brackets, which is like multiplying out of 1. And then I get 4 plus x, and then the 4,
Yeah.
and then the x cancels here.
Okay.
Infinite limits, this refers to limits that have plus or minus infinity as the answer. For these, knowing the graphs of things are very useful. Which is why I've been testing you on graphs since day 1. Functions are very useful. Right, so I've showed you a couple of common ones already. So this is like example limit as x approaches 0 of 1 over x squared is what we would call an infinite limit because the answer is infinity. I could also talk about something like the limit as x approaches 0 from the right of ln x, and that answer is negative infinity. How would I know that's negative infinity? Well, I know what the graph looks like. Right, that's y equals ln x. As I'm approaching 0 from the right side, it keeps going. So that answer would give me an infinite answer, and I know that it's negative infinity because I know the graph. I can see the behavior of what it does. Right, so those are called infinite limits. Limits where infinity is the answer. It is a valid answer in our course. Infinity is not always a valid answer everywhere. There are some textbooks where it's like, if the answer is infinity, say it doesn't exist. But for our purposes, it does. We want to know when something is getting huge or getting super small. Super negative. There are also limits at infinity. And these are all super important as well. These are limits taken when the x values we actually let approach plus or minus infinity. So I could ask you questions like this. What is the limit as x approaches infinity of 1 over x? Or what is the limit as x approaches infinity of e to the x? What is the limit as x approaches minus infinity of e to the x? What is the limit as x approaches infinity of e to the minus x? So notice that when my x itself is going to an infinite answer, either plus or minus infinity, I could want to take a limit like of that form. So what do you think the answer would be? Here I don't enter it. So remember, what's the limit? It's the y value. We're tracking the y values. So of course we have to talk about what does it mean that x approach infinity? It just means you're going far to the right. You just go to the right. You keep going. Just go. Right? Just go to the right. Like as far as possible. When you think you're there, keep going. Right? So you keep going to the right and you're looking. What is happening to the y values?
Increasing.
They're decreasing out to where? It's approaching 0. Now, it never actually gets to 0, which I don't care. Limits don't care about being there. It cares about what you're getting close to. So as I'm getting, my x value is getting larger and larger, my y value is settling at 0.
Yeah.
So I can say that this is 0, right? And x approaches infinity just means x gets larger and larger and keeps getting larger. Right? And then you're looking at what is happening to the graph as my x gets larger and larger. Right? So for example, with this function, e to the x looks like that. Right, so what happens as x approaches infinity of e to the x? What's happening to the y values? They keep getting higher and higher. They increase without bound. I can say that this is infinity. Again, we have e to the x. But now I ask a different question. X is approaching negative infinity, meaning x gets smaller and smaller, more and more negative. What's happening to the y values? As I approach, go far to the left, just go, keep going left, go, just go, right? Never stop. This is decreasing to 0. Again, it's trying to level off at 0. So that would be 0. So for e to the x, as x approaches infinity, the answer is infinity. As x approaches negative infinity, the answer is 0. What about e to the minus x? What is the picture?
Reflect over the axis.
This reflected where?
The axis.
No, over the y-axis, right? The negative in front turns things upside down. So that would look like this. And so what would that be? That would be 0. That's the answer. So we talk about limits, what it means. You're just factoring y values. Sometimes the answer can be a number or it does not exist. Sometimes it could be infinity. The answer is infinity. We say it's an infinite limit. If you want x to go to infinity or negative infinity, we say it's a limit at infinity. That's the terminology. And especially for infinite limits or limits at infinity, knowing the graphs is going to be a super important tool in being able to compute them. Just a word on proper notation. I should mention this because I will punish you if you don't pay attention to it. So, here's one big thing you want to keep in mind. Keep writing the limit sign until you actually take the limit, meaning plug in the x value or simplify to a point where you can plug in the x value or something like that. Right? It's very important that you know when that point happens. So again, as I was saying, you'll notice from the last example I did with the rationalizing, I kept writing the limit until the point I actually plugged in 0. No, you have to write the whole. So we have limit as x approaches. Let's do something like x plus 1 minus 1 x, x equals 0. So, what do I do here? Right, obviously, I can't plug in 0 because I'm divided by 0. So I'm going to want to try to fix this. It's a complex fraction, so I'm going to multiply or divide by the LCD. Multiply by x plus 1 over x plus 1 equals limit as x approaches 0. So notice I haven't plugged in x equals 0 yet, so this I have to write. I have to keep writing it until I actually do it. So this, when it multiplies out, the x plus 1 cancels and I'm left with x. This, when I multiply out, the x cancels and I'm left with x plus 1. Over here, x times x plus 1 equals limit as x approaches 0. Keep writing that because I'm not plugging in 0 yet. I can't plug in 0 at this point. So the top.
So x minus x times 1. So negative 1.
I think there's something. Is that where I want to? X approaches 0, that's
It should be. No, it's right. On the should be.
I think this was a 1. Yeah, that's what I'm thinking of something in another chapter, that's what. It's a random example. It's my example. I can do what I want. So in this case, the LCD will be x plus 1 over x plus 1. In which case, when this multiplies that, I will get 1 minus this multiplies that, I get x plus 1 over x times x plus 1. And so now it's gonna, I can't plug in x equals 0 yet, so I write this again, and I'm going to simplify this. I have 1 minus 1, and on top I have minus x over x. And now I can cancel the x's. So this is limit as x approaches 0. Write it again of minus 1 over x plus 1. I write it because I didn't plug in x equals 0 yet. And at this point, I can not write it anymore. Right? At this point, I don't write it. Since we plugged in x equals 0. So I actually took the limit here, right? So this whole time I'm just simplifying. This guy has to hang out because I need to remind myself I didn't take the limit yet. I didn't take the limit yet. I didn't take the limit yet. Yep. Boom. Now we're at a point where we can take the limit. Shoot. Right? So here you're just aiming, and then you actually take the shot right here. So you stop right at that limit.
Why don't you just write every one?
Come in.
Why don't you just write every one? You go negative 1 over 1.
It's negative 1.
Yeah.
You know what?
Well, I want to emphasize that there was a 0 plus 1. I hate if you guys put math together. You're like, "Oh, you should have put negative 1 minus that. Jeez, chill, bro. I think we'll stop there. So, next time we'll talk about why we care about limits. We're going to talk about continuity, and we're going to finally get to the derivative, I think. The quiz on Tuesday will be everything up to the end of chapter 1. I won't quiz you on chapter 2 until after. Oh, by the way, there's homework posted. I don't know if you guys saw it. It's due on noon the day of the test, but I try to get it done before that in case you need to ask questions about it.
We have homework the 20th and the 23rd. And we have a quiz on chapter 1.
The quiz on chapter 1 on Tuesday. The test is no chapter 2 on the quiz.
Chapter 1.
No, what I did between the last quiz on chapter 1 and the new quiz on chapter 1. So it's like chapter 1.5 and 1.6. So like, but you're going to have to know the whole of chapter 1 for Thursday, so you might as well prepare for everything.